Hi everyone, so this is the second part of the heat and first law of thermodynamics chapter where we're actually going to talk about the first law of thermodynamics. Um, so, as we mentioned before, there's a relationship between heat and energy. Actually, heat is a type of energy. So, we're actually going to kind of talk a little bit more about that. Um, because not only can heat flow in order to cause temperatures to change, it can actually be related to the work being done. So, what we have is this equation. This is actually the first law of thermodynamics equation that the internal energy within the system, basically how much energy the molecules end up gaining, is based off of Q, the heat added to the system, and minus W, the work done by the system. Now, one thing that I really want to stress is that this equation will change if you look online. When you go online, you might see it as Q plus W. The sign convention is based strictly on what you're defining work and heat. Because a lot of times you might see something like Q plus W, where W, the work, is being defined as the work done on the system. You might see Q being negative, where Q is the net heat lost, removed from the system. So the sign really is based off of the definition. So the definition we're using is that the numbers we're plugging in are positive if Q is added to the system and if W is done by the system. Now to kind of clarify a little bit more about what does that mean, work done on and work done by a system, the best way and the reason why we're setting it like this is to think of steam engines, in particular a piston. So in here, imagine you have a canister, and inside the canister there's a gas. As gas is added to the system, it will end up expanding and contracting based off the PV equals nRT equation. And what you'll have is based on that expansion, it will end up causing the piston to move. So heat gets added to the system, and either it doesn't do any work to move the piston, where so in that case all that heat turns into internal energy, or it could cause the gas to expand a bit and lift that piston up. By lifting it up, it's doing work. So that's what we mean by work by the system. If, on the other hand, you're doing work on the system, then when you add in heat, you would also have to be pushing that piston down. Actually, you don't even have to be adding in heat. You just push the piston down and compress the gas, and that would be work done on the system. Based off of this equation, that would make that work negative. So if you did 500 joules pushing a piston down, when you plug it into here, it would be a negative 500. Um, Now, one thing to note is that these are not state variables. These are not like things about the system itself, things like pressure and volume and temperature, but really more of how it goes from one state to another. So, like I said, heat, and we're talking about the heat and work being done on the system. And while we know that the work being done on or by the system is based off of the expansion and contraction of the gas, well, we don't have any equation that's talking about that. So that's what state variables, these are what we call state variables. This is not dealing with that. Um, but it is dealing with how we go from one state to another. Now, another way that this could be written in a little bit more of an expanded way, because of the fact that this is a conservation of energy type equation, we can actually include this to not only be about change in internal energy, but change in kinetic and potential energy. So try that question here, pause the video, work on this stuff, and we'll go over in a second. All right, so here we want to figure out how much energy, how much the internal energy changed. So we use our equation, but we have to double check with our sign. So here, this is heat added to the system. So no, I don't have to put a negative here. I just put it in for Q. But this 1800 joules is work done on the system. So that means when I plug it in, I have to make it a negative number. So all together, the energy is going to end up changing by a little bit over 4,000 joules. And again, it's the work is negative because it's done on the gas and not by the gas. It's being compressed and not expanded. All right, here's the next question. You can pause the video, work on yourself, and we'll go over in a second. All right, so here we're going to use that slightly expanded equation. For the most part, you're probably not going to be working on too much. But here we have a change in kinetic energy. There doesn't seem to be any work being done. There's no heat being transferred. They don't mention anything about a temperature change, and they don't mention anything about, you know, something being moved. All we have is a bullet moving. Well, yeah, they have that moving, but I mean like a piston moving or the bullet moving something. So the equation ends up just being the change in kinetic energy and the change in internal energy. So taking these two things, we just figure out how much the kinetic energy changes. Note that I'm not just going to do 1 half m delta v squared. I have to actually do vi squared and minus vf squared. From here, plug the numbers in, and we end up getting that the internal energy changes by 180 joules. That essentially the energy gained by the environment, if you will, ends up the molecules end up moving faster by 180 joules. All right. Now, there's a bunch of processes that we're going to talk about. So as we mentioned before about the whole state variables and how like heat and work kind of is related to that, we're going to deal with that right now. So one thing that you're going to note in this topic, but definitely especially in the next topic, are these PV diagrams, which is relating these processes that take us from one state to another using internal energy, heat, and work. So the first process that we want to talk about is the isothermal process. The name isothermal means same temperature. So the process means that we're going to go from one state of pressure and volume to another state of pressure and volume. But we're not going to change the temperature through that process. So here's two examples. You have a state A, B, A prime, and B prime. So going from A to B is one isothermal process. A prime to B prime is another. It's the same shape, but different location due to the lower temperature. Sometimes you might see these curves being called isotherms. Now, the way an isothermal process usually is done is that the system that you have is in contact with something called a heat reservoir. The heat reservoir is something that is such a massive body um, that that is able to. It's so massive that it can maintain its heat despite any transfers of heat. Sorry, it can maintain its temperature despite any transfers of heat going into or out of the system. So here, they actually they don't have it here, but if we had this piston connected to a gigantic burner that was held at a very stable temperature, then as we moved and pushed and pulled this gas while it's in that contact, the gas won't change its temperature because it's still going to be in contact with that heat reservoir, so it will always maintain that same temperature. Now, because the temperature remains the same, that means that our internal energy has to also. Oh, sorry, because the temperature remains the same, that means that our internal energy doesn't change because the equation is 3 halves nRT for the internal energy. So the change in internal energy is just that with delta T. So it ends up being equal to 0. That ends up being a very important aspect for the isothermal process. That internal energy remains 0, and that it doesn't change. I should say it like that. The change in internal energy is always 0, and that also means that the heat added to the system is equal to work done by the system. So again, going back to that concept, here any heat being transferred to the gas is causing the piston to move up by an equal amount of energy. The next process is something called the adiabatic process. Now, the adiabatic process requires no heat to be transferred. That's the big thing here. Typically, the way an adiabatic process works is that the process is done so quickly that heat doesn't get the chance to transfer. Because remember, heat is usually transferred through the bumping of molecules from one material to another. So you just immediately take it from one state to the next state in a very quick way, and it won't have the chance to transfer heat. Now, here is an example of how the isothermal process and the adiabatic process will end up looking different. Note how there's no time aspect to here, so there's no way of noting whether or not it's going quicker or slower. But you can note that it's going to a different location than the isothermal process. Here, what we end up getting is that because the Q ends up being zero, our change in internal energy is going to be equal to the negative of the work being done by the system, or another way of saying it is how much work is being done on the system. So internal energy decreases when the gas ends up expanding. And this is kind of one of the ways how diesel engines end up working. The reason why these processes are going to be important is because in the next topic, we're going to start talking about engine cycles, and that's going to require this concept and understanding of the different processes. Now, these two are fairly easy, so I'm going to explain them both together. The isobaric and isovolumetric processes. Isovolumetric is sometimes called isochoric. Isobaric, same pressure. Isovolumetric, same volume. As the name implies, the pressure doesn't change, volume doesn't change. Easy peasy. Now, each of these, we can end up finding out how much work is being done through the process. And we can also come up with equations based off of their state variables, because that's going to be something that's important. So what we're going to do really quick is just consider this a gas in a canister. And we want to know how much work is being done when the gas expands quasi-statically. And we're going to make sure assume that P and T are uniform. Now, what we mean by this is that it's going to expand in such a way that it's always going to be in I want to say, for lack of a better word, in a constant uniform state. This will kind of make sense in a bit, hopefully. If not in this topic, I'll mention in the next one. All right, so since pressure and temperature are uniform, we can use this equation, F equals PA, because we know how much force is being exerted onto the piston. The work being done is basically this pressure times how much that piston's being lifted. So what we end up getting is this. Now the pressure, because it's uniform, we're going to assume is not changing in this case. So what we can combine the A and the DL to become dV. Now the way that we find work is by taking this equation and integrating it between the two volume points. Because even though the pressure is, well, actually the pressure doesn't remain same. That I misspoke there. It's uniform, meaning it's going to be the same value throughout, but it's not constant throughout. Because of that, we have to actually go back to PV equals nRT and plug that in to this equation. So that way we get the relationship to volume. nRT are constant, so they get pulled out. So we integrate dV over V, which, as many people who know calculus know, that's a log function. So what we end up getting is, in this case where the temperature is remaining constant, a isothermal process, this equation is going to be how we find the work. Now, if we look at the graph for an isothermal process, this essentially is us taking the area under this curve. That's kind of what we're doing here when we do the integration is we're taking the area from point A to point B, and that's the work. Now, that as you can probably might be able to guess, some of the processes that we've talked about are going to be easier to find work than others. But for now, this is one equation that we have for the work for an isothermal process. Now, if we look at this situation, we're going from A to B. We have two different ways to go. We have the isothermal way and the isovolumetric isobaric way. Now, if we look at this scenario, going from A to B through this process, we can already tell that the isovolumetric is going to require no work. The reason I know that is because going back to my definition, it's the area under these curves. This is a straight line up and down that it has no area. Another way of thinking about it is that the dV equation is zero. So when we integrate p dV, well, dV is zero, so the whole thing ends up being zero. So this isovolumetric section is always zero. And that's something that's always going to be true. But the isobaric will end up having a amount of work being done. So if we go back to the equation of it being the integral of p dV, now pressure is going to remain constant. So here I can actually pull it out from the integration, and then I'm just integrating of dV, which just turns into VB minus VA. Now, one way that we can rewrite it if we wanted to kind of make it look a little bit similar to this, is we can then, if we take out, since this is the pressure at state B, we can actually divide VB from out of this setup. So that's in with this PV right here. And then from here, we can actually rewrite this as NRTB, and then times by this relation. So this is the work done in the isothermal case, and this is the work done through the isobaric pathway. So even though we're going from one state to the exact same state, based off of the process that we take, it's going to change how much work is required. So this ends up being an important aspect, and it's kind of like I said, how the main way that we're going to do with engines, because we're going to go from one state to another, and then we're going to go back to that state using a different process, allowing us to get a net amount of work out of the system. And yeah, so it's based off of the type of process or the path based off of that. All right, so here's a practice question that you can work on. Pause the video, work on yourself, and we'll go over in a second. So we want to know how much total work is being done by the gas as it goes from B, D to A. The way we're going to end up doing this is using the equations that we have. First, we have to kind of convert a bunch of numbers. So they give us the numbers in atmospheres and liters. So the atmospheres get converted using this equation, multiplying it by 1.01 times 10 to the fifth. The liters are going to be a little bit different. You have to remember that 1 liter is 10 to the cubed centimeters cubed, or another way of writing is 10 to the negative 3 meters cubed. If you have any questions as to why this is, please let me know as soon as possible, because it's something that you need to be able to do. Very quickly, I'll just say that when it's centimeters cubed, centi is times 10 to the negative 2, but that has to be cubed, so you have to do times 10 to the negative 2 3 times. Now, during the process BDA, the work is only done during this process from B to D, BD, the isochoric process. And as we know, it's just going to be PdV. So we have the pressure, we know what the volume is going from 10 to 2, plug those numbers in, and we get the work ends up being negative 1.6 kilojoules. So this ends up being the amount of work done by the gas. Because it's negative, that means the work is actually being done on the gas rather than by the gas. All right. Now they want us to figure out the heat flowing into the gas. So one way that we could do that is, since we know that A and B is an isothermal process, we know that the states between A and B, the internal energy doesn't change. So regardless of whether we're going from A to B or B, D to A, we know that by the end of this entire process, this run, as I go from B to A, um, the internal energy is going to be staying the same, meaning that the heat added to the system and the work done by the system are going to be the same. So plugging these numbers in, we end up getting this. So we get that the heat flowing into the gas is negative 1.6 kilojoules, or the heat ends up flowing out of the gas again because of that negative. All right, here's the next question. You can pause the video, work on this stuff, and we'll go over in a second. All right, so here we have a process that's expanding adiabatically. The temperature is going from one temperature to another, and they want to know how much work is being done. So we know that um, the because it's an adiabatic process, we know that no heat is being transferred. So that tells us that the internal energy and the work being done are the same, are equal. Um, so all we have to do is just figure out what the change in the internal energy is, and that tells us how much work is done by the gas. So using that equation, the 3 has nRT, or delta T, plugging the numbers in, we end up getting negative 2,300 joules. Because work is the negative of the change in internal energy, we're gonna have to negate that, and we get the work is 2,300 joules, or the work being done by the gas. This is a really nice table to have. I recommend that you write it on a separate sheet of paper and you kind of have it with you for whenever you're doing these processes. It's important to know what the process is working with, what ends up being constant, and essentially, what about the first law is zero, and which energies are going to be equal to each other. So this really kind of condenses everything we've talked about. All right. There's a thing called a free expansion. So, and we're going to talk about the work done for the adiabatic process as well. So, for a free expansion, the main thing here is it's sort of like the adiabatic process. Um, and here, the internal energy of the gas doesn't change. So, what you end up having is basically everything zero. Um, so, it's a type of adiabatic process. The best way to kind of explain this is that it's imagine you have an isolated system. So because it's an isolated system, heat can't be transferred from one point to another. So heat can't be added, heat can't be removed. You have a vacuum on one side and a gas condense on the other. You release the gas. You release this valve, allowing the gas to freely expand into the next spot, but it's not moving anything, so it's not doing any work. And basically, what that tells us is that the energy of the molecules isn't going to change. Um, Now, in this is a of course an ideal gas. This is a theoretical thought concept. It actually is found that in real gases, and this actually pertains to all the processes, that real gases actually do have slight changes to these things. So, for example, during this expansion, there is going to be a slight change in temperature, or based off the pressure and volume. So that the internal energy will change a bit. And like I said, that's also kind of true with the isothermal case and the adiabatic case, that it's not really going to have no temperature change, it's not really going to be no heat change, but it's a good approximation of what's going on. It says here that the free expansion can't be plotted on a PV diagram, but technically nothing can be plotted on a PV diagram. Like none of these processes in real life can be done, uh, because the PV diagram is assuming that at every moment it is maintaining an equilibrium state. But what turns out is that as the gas is expanding or contracting or changing its temperature or whatever it's doing, there are going to be peaks and divots, and some areas are going to change values and some are going to go in the other way. So it's really hard to kind of graph a real gas going through these processes. I just want to mention really quickly this concept of molar specific heats. Um, so it turns out that the specific heat of a gas actually depends on which process is going on. In particular, the two are constant pressure and constant volume, specific heats. And because it's gases, it's easier to kind of deal with molar specific heats rather than a mass. So the equation doesn't change. It's still the same thing. Instead of m little c delta t, we kind of combine the m in with the c, and we end up having this little n capital C. So capital C is our molar specific heat. Little n is going to be the number of moles. Another way of writing it would be that if we want to go back to you know the little c term, we would have the molar mass of the gas times the little c specific heat. That's pretty much it. Again, molar mass is just the mass of the molecules divided by the number of moles. But for gases, it makes a whole lot more sense to talk about moles rather than mass. So that's why we end up using this instead. Now, one thing to note, there actually is a very unique relationship between the specific heats. First, if you look at the molar specific heats of pressure and volume, the difference between these numbers is always the same. It's always a difference of two. In fact, you may notice that um, okay, not so much for this one, but for this one, the molar specific heats are pretty much roughly the same. So for helium and neon, the molar specific heats are around 3. These are around 5. These are around, well, these are around 5. These are around 7. About, 8 or 9, 6 or 7. Kind of gets a little bit wonky here. But the interesting to note here are these two things, that the difference between the volume and the pressure is always pretty much 2. So that's going to be the same regardless of whether we're talking about monatomic, diatomic, or triatomic. Um, and not only that, if we divide these two terms, we get this ratio, which we call gamma, which is always the same based off of what type of how many molecules it is. So monatomic gases all are given 1.67 as a specific heat ratio. Diatomic are all 1.4 and triatomic are all 1.3. Um, there is a reason for this. I don't know if I'm going to go over it completely. I might in the next video. But if you want me to explain it, I can go through it very quickly in one of the video classes, or you can ask me on Remind. But you want to know those gamma terms and how it relates to each of those types of atoms, because it will play a part in a bit. Um, all right, so we're going to briefly kind of show some of that relationship right now. So if we go back at a constant volume, If you remember, when the volume is constant, the isovolumetric case, there's no work being done. So through our first law of thermo, we know that the heat added to the system has to be equal to the change in internal energy. So we have this. For the other case, the constant pressure, the equation actually turns into this instead. Just moving the work to the other side. Both of these are just taking the first law of thermo. Um, when we combine these two, subtract them, we actually end up getting this, that the difference in the heat at constant pressure and constant volume is going to be equal to the work done in this constant pressure case. When we use the equations for NC delta T in for both those heats, we end up getting this. And because we have a gas, we can actually replace it with PV equals nRT to get this. The moles drop out, the change in temperature drops out, the pressure drops out, and we end up getting left with this, Cp minus Cv equals R. So right here, we can already see why the difference between Cp and Cv is always the same value. Because according to this, no matter whether we're talking about monatomic, triatomic, diatomic, the difference is always going to be equal to R. So what we have here is that if we look at a monatomic gas and we kind of, you know, look at this equation, plugging in the whole 3 halves nRT and solving for it, we actually get that Cv equals 3 halves R, which means using this, we could figure out that Cp is going to be equal to, I don't know if I have it on the next slide, which is why I'm mentioning it, would be equal to 5 halves R. All right, so this is going to lead into something that we call the equipartition of energy. So I mentioned before that that equation for the monatomic gas of 3 halves nRT is specific for monatomic based off of the type of energies allowed. This is because translational kinetic energy is only allowed 3 degrees of freedom. Um, Motion in the x, motion in the y, motion in the z. But as we said before, when we get more molecules involved, translational won't be the only degrees of freedom we have. We also will have rotation and vibrational. The equipartition theorem of energy basically says that energy is going to be equally divided between every active degree of freedom allowed. So, for example, with monatomic gases, only 3 types of energy are allowed. So we have 3 degrees of freedom, and the energy is going to be equally divided between those 3 energies. Um, it actually turns out that each energy is allowed 1/2 kT of energy. Going back to the equation for the internal energy, the reason it's 3 halves is because there's 3 degrees of freedom, each one gets a half. I'm not going to go into why this is, but basically the short answer is quantum mechanics. Now there are two extra degrees of freedom for rotational energy. So basically that equation will actually turn into 5 halves nRT or kT, and then the higher than that would be 2 more vibrational kinetic forms of energy, bringing it to 7 halves. Again, pretty much all that's going to do is that's going to change that front coefficient. Now, one thing that you may notice is that they might have you dealing with a triatomic molecule, but they'll throw in a phrase that is meant to kind of say that we're going to kind of ignore the whole rotational vibrational aspect. What they'll say is that it's at a low temperature, essentially. So if you see here, if we had a triatomic gas, let's say, so we had something like a water molecule, even though it could technically reach vibrational kinetic energies, um, at low temperatures, the molecules are actually only allowed translational kinetic energy, which does kind of make sense because at these low temperatures, for at least for some materials, I don't know if this is specifically, actually, it's not really water because that's not a gas at this point, but at low temperatures, um, they're only really allowed translational kinetic energy. They don't really have enough energy to kind of rotate and vibrate. But then as you increase the temperature, you give it more energy, it will end up allowing for these additional things. So they could always limit it and say, even though we're dealing with triatomic gases, we're still only looking at this translational. So they're only changing the mass and not necessarily changing that 3/2 coefficient. Just want to throw that in there, just to be safe. So if we look at the adiabatic process, the equation we have is this. Again, the adiabatic process, there's no heat being transferred. So that internal energy that's changing is going to be equal to the change in the work, which we already know is PdV. We already know that um, at constant temperature, the internal energy is going to be related to this. So we can kind of combine these two together and say that the internal energy, the change in internal energy, and the PdV is equal to 0 because, move this over to here, that gets added. Now we're just going to play around with this and bring in some equations. So we know, and the ideal gas law tells us PV equals nRT. So if we actually separate this and we do a partial derivative based off of all the variables, because there are three variables that could change: P, V, and T. So this has to be split into two parts: PdV plus VdP. But this just kind of gets left as dt. From here, we can just solve for dt, and this is going to be brought back to this original equation. It's going to look like that. The n's will end up dropping out. We can basically just fool around with this, combine the dv's on these two sides, have the dp on the other. We can actually combine this. If we remember that the difference between CV and CP is R, we actually combine this into CP. And then, yeah, we're just going to keep playing around with this. So divide the CV from both sides so we get this relationship. This CP over CV is going to be simplified as gamma. And then what we can do is divide both terms by P and V so that we get dV with V and dP with P. From here, when we integrate this, it's going to give us this equation, gamma ln V plus ln P, because that's what the integral of dV over V is. And then the integral of 0 is always a constant, which is going to leave us into this. Raising both of these to the E, or to some power, we end up getting this. So PV to the gamma for any adiabatic process is always going to be equal to a constant. So the way that we're going to use this is that when we have the two states for the adiabatic process, the initial and the final, one set of pressure and volume and another set of pressure and volume, we can use this equation and say that the initial pressure volume to the gamma is equal to the final pressure volume to the gamma. And it can allow us to figure out what that final volume is, or final pressure is. One thing to note, it is only the volume that has the gamma. It is not gamma, it's not this entire PV term raised to the gamma. It's only it's only volume raised to the gamma. That's going to play a much bigger part when we start dealing with the engines. Alright, so pause the video, work on this stuff, we'll go over in a second. Alright, so they want us to figure out what VB is, and they want us to figure out how much work was done on the gas. So going from A to B, we know that this is an adiabatic process. We have the volume and pressure of A. We know what the pressure is at B. We just don't know what the volume is. So we can use that relationship that we have. The one thing to note, it's a monatomic gas, so we already know what gamma is. It's going to be 5/3. Um, so from here, we have this. Um, from setting the values for state A and state B equal to each other, moving it around so that we're solving for VB, plugging our numbers in. I don't have to actually convert these values as long as they're in the same units. And we end up getting that volume at B is 0.66, which does kind of make sense. It is in between zero point 0.5 and 1. All right, the next part, finding the work being done on the gas. So we're going to do the whole process. We already know how to get from B to C, the work done that way. We just kind of have to come up with an equation going from A to B. So what we have to do is kind of go back to our definition of how we found work. We always found work by doing the integral of P dV. So at any single point along this process, we know that this is going to be true. That P V to the gamma for state A times V to the negative gamma for any other point is equal to P. Plugging these in for here, pulling out the PA and VA out, leaving us with just this. This integral ends up turning into this. There's actually no ln here. From here, we just kind of fool around with the equation. You don't have to worry too much about what I did here. Just try to, again, move some things around. Plugged in the numbers that we had, and we get 48 kilojoules. So that's only to go from A to B. Now going from B to C, we actually could go back. I don't know why I'm redoing it here, because we have an equation for an isothermal process, but this is kind of just re-showing how we do it. Again, we're using ideal gas all this time. This time we get this as our equation. We plug the numbers in and we get 37 kilojoules. So altogether, the total work is going to be 55 kilojoules. All right. So I mentioned before that there are other types of heat transfers where mainly we've talked about conduction. There are other ways, and there's also other things about conduction and these other types that we kind of glossed over. So as I said before, that the whole concept of heat conduction can be thought of through that kinetic theory process by imagining the molecules of one item bumping into and basically speeding up or increasing the energy in the other molecules. And as we know, momentum is conserved. So every time one molecule in the hot spoon interacts with the cold liquid, as it increases the cold liquid's molecules up, it's also causing the spoon to decrease in its motion. We have an equation for that actually relates to how quickly heat gets transferred through a system. So this was something that we didn't really talk about. We talked about how much heat gets transferred, but not really the rate at heat being transferred. Because as we know, there's a difference between it, even though we can know how much heat needs to be added to water to heat it up, we may not know how long it takes for it to heat up to that point. So that's what this conduction equation is. The rate at which heat is being transferred through a system through conduction is based off of its thermal conductivity, the cross-sectional area of contact between them, the temperature difference, and the length. If you go through this equation bit by bit, all these kind of make sense. You have a large area of contact. Clearly, you have a lot more areas for molecules to bump into each other, and that will allow for heat to transfer quicker. But if you only have a small area of contact, like a little finger touching on something, there's only a small bit of molecules that can touch. Of course, temperature difference will also allow for heat to transfer much quickly, because if the molecules in one item is going significantly faster than the other, then it's going to allow for a lot more energy to be transferred through each collision. And then the length, again, that also does kind of make sense. The longer heat has to flow through the material, the longer it's going to take for it to have to, transfer that heat eventually throughout. One thing that's actually really interesting to note is how this plays into how an object feels. If you've ever noticed, when you touch like a metal object that's been sitting outside for a bit, or not outside, but just like at room temperature, if you ever feel the metal, it always feels colder than something like plastic or wood. It's usually how you can actually tell that something's metal versus something else. Now, the reason for this is actually because something like steel has a much higher, or silver has a much higher thermal conductivity than wood. So that means that it allows for heat to transfer much quicker, more quicker, um, more quickly, I should say. So you can actually test this at home if you have it. You can leave two objects out at room temperature for a bit. One piece of wood and one piece of metal. If you have one of those nifty little thermal guns, you can kind of point it at and make sure that they are at the same temperature. And if you touch them, you'll notice that the metal always feels colder. The reason being is that it feels colder because the thermal conductivity being so high allows for heat to be removed from your hand a lot quicker. So your body assumes that because the heat rate is so high, it's got to be because the temperature difference is higher. That you're at a much higher temperature than the metal. But it turns out it's mainly because that thermal conductivity is higher, as opposed to something like wood or air or goose down. Um, so the last thing I'm going to mention about thermal conductivity is this. Typically, items that have a very large K value that allow for heat to transfer very quickly are usually called good conductors, while the materials that have the small K values are usually referred to as insulators. Now, there's no like set scale of what exactly makes a good conductor and what makes a good insulator. Typically, you're always referring to a relationship to something else. So, for example, silver is a better conductor than copper because it has a higher K value. But you can't say that copper isn't a good conductor, it's just not as good as silver. This is kind of how materials need to be made, like in houses and stuff, to kind of keep track of this. So here, pause the video, work on yourself, and we'll go over this in a second. So here we want to know what the heat flow rate through a window is. So just plug and chug into that equation we have. Nothing really crazy. You have to get the K value from the book. I didn't put it up here. But you get that the flow rate is about 790 watts, or joules per second. Now, typically for building materials, it is a little bit more complicated. They have something called an R rating, which is really kind of referred to through their yeah, usually based off of thickness. And again, it usually is referring to things of like how well it can insulate, essentially. So a lot of times, higher the value, more insulation you get. All right, we're not. I'm not really going to talk about these other types. They're kind of pretty basic and very niche, so you're probably not going to deal with it unless you're dealing with, unless you start going into something like HVAC or earth science, like meteorology type stuff. So I'm just going to quickly mention Convection is a type of process where heat's being flowed through the mass actually moving from one point to another. So, unlike before with conduction, where you had molecules bumping into the next part, but you didn't actually have it transferring, like the molecules in the spoon didn't actually transfer into the glass. Uh, Here, we actually will have molecules moving from one point to another. Usually, another difference between conduction and convection is with convection, it's the same material and how heat is being transferred throughout that material, while conduction is going from one material to another for the most part. With convection, you end up getting these things called convection currents. So you end up getting like this motion of like you know, the hot materials rising and then the cold materials falling down due to the difference in densities and stuff. Sometimes called Bernard cells. Like I said, mainly this is how what you would do in meteorology for weather patterns and stuff like that. So not really going to go that much into it. Radiation, I'm going to go even quicker through that. Um, so here, there actually doesn't need to be any sort of medium with radiation. So again, with conduction, you have to be in physical contact, but no mass got transferred. Convection, the heat was being shifted throughout the medium, but with radiation, it's going from one point to another without any sort of thing. This is how the sun actually transfers its heat. Um, the heat rate is given by this equation, which is called the Stefan-Boltzmann equation. This sigma term is just a constant term, and then E is a coefficient that we call the emissivity, which is a basic characteristic of the material. The value goes between 0 and 1, and essentially it's how well the object can emit energy. So, dark surfaces, something that can actually absorb energy very well or emit energy very well, is very close to 1. And this is actually where black body radiation ends up coming into play. Um, and oh yeah, something that has a 0 would be like a good reflector. Um, yeah, so this is another way of it writing, dealing with going from one type of temperature to another based off of surrounding temperatures. You can practice this yourself. I'm not going to put this up, but if you want, you can pause the video, work on yourself, and we'll go over it real quick. For the most part, it's a plug and chug. That's pretty much it. They give you all the numbers. You just plug them in, and you chug out an answer. It's 120 watts. Um, this actually ends up getting used sometimes when we're dealing with planetary stuff. It actually can be used to figure out distances of stars and such. We have something called solar constant, which is 1350 watts per meter squared. Yeah, it's also the angle also affects the amount of heat that ends up getting onto the object. It's why the tilt is what causes the seasons, the summer and the winter tilting away and towards whatever. It's not actually the distance. Ironically enough, if you didn't know, when the north has summer, we're actually further from the sun. So that's one way that we can actually tell that it's the tilt and not the distance. Another question that you can work on, pause the video, work on itself, go and we'll go over it. Not needed though. You can skip it. Okay, once again, plug the numbers in to the equation. Here, we're just gonna take a ratio between the two locations and then we end up getting this. Yeah, so it's not really a perfect answer, but um, at least it gives us a rough idea. All right, so the summary that we mainly talked about the internal energy equation. That was definitely really important. And as I mentioned, this three halves really only works for the monatomic gas. If we deal with diatomic, it becomes five halves, triatomic, seven halves. The heat, when heat is used to change the temperature, we use MC delta T, but when it's used to change phase, it's ML. Make sure that you separate the steps. It changes temperature, then it changes phases, and then it can change temperature again once it's in its new phase. We also talked about finding work on gas, and we looked at a bunch of pressure and volume graphs. These are the homework problems that are going to be due Wednesday. Again, check Blackboard to see the exact date. Um, and yeah, that's pretty much it. If you have any questions, please let me know. Otherwise, I'll see you in the next video.